So I've written pseudocode here for what a top-down approach might look like. And so in a top-down approach, what we do is we start at n, and we identify the subproblems which would give us the answer to n. We go solve those subproblems, and then we repeat. And we hope that somehow by doing it this way, we can skip solving all the subproblems. Like maybe we'll never have to figure out optimal change for for 5 or something like this. Maybe we can just find optimal change for 6 by identifying optimal change for the other ones, for 4 and down, and we can ignore 5 or something along those lines. So the approach goes like this: you initialize n as a 0 to n size array. So there's little n plus 1 items in the array. And so suppose n is 6, then our array will look like this. The first one is 0, right? The 0th position is 0, and that means that it takes 0 coins kind of by definition to make optimal change for 0. And then I'll put -1s everywhere else. -1, -1, -1. And so what -1 means, if it's in this array, is that we haven't solved the related subproblem yet. Okay? And so the indices here are 0, 1, 2, 3, 4, 5, and 6. And so when the problem begins, we haven't solved any of the subproblems. Okay? So now how do we do this? Well, to solve we write this code now that interacts with these globally defined arrays, D and N. And so now this code is recursively defined. And so you notice that it has a recursive call right here. So what it will do is the first thing it does is it asks, hey, so change of I is trying to identify optimal change for I. So the first thing it asks is, do we know this yet? Do we know optimal change for I yet? And it asks this by checking to see if the corresponding entry in the n array is negative. So if the corresponding entry is negative, then we know we haven't identified optimal change for this value of I yet. So now we know we better go do that. Okay. So now just suppose we're here. So what this does now is it says, all right, my job is to identify optimal change for 6. So now what I'll do is exactly the same thing as the other code did, the other bottom-up algorithm. I'll go and I'll compare all of the different possible values I could get for different change amounts. And so the first thing I'll do is I'll find optimal change for 5. Right? That's what happens when j is 1. So j is 1 puts me here. And then I'll find optimal change for 3. So j equals 2 puts me here. And then j equals 3, the third denomination, puts me here. So after our first pass on this thing, essentially what we've done is we've said, hey, we've got to go find optimal change for 3 different values, for 5, 3, and 2. Okay, so each of those now is a recursive call. And so what we'll do is we'll go check our array. We'll call recursively on this function change. And what change does is it looks at the array and figures out whether or not that item has been identified yet, that change amount has been identified yet. If it has, it just returns it. But if it hasn't, it goes in and computes it. Okay, and so when it goes and computes it, it performs more recursive calls, and on we go. Right, away we go. And so it's kind of hard to visualize exactly how this algorithm is going to run just writing out the array like this. So in a second, I'm going to write a full recursion tree for the full search for optimal change for 10, and we'll see if this algorithm saves us any work. But this is essentially how it works: is we start at our target number. And then, because of our DP idea and because we understand the DP idea, we know which subproblems need to be solved. And so then we go solve them. But before we solve any of them, we check to see if they've already been solved. And that's kind of the interestingness of the top-down approach, is that we solve precisely the subproblems that need to be solved to get us the answer. But before we do any work for each of them, we look up in some global table whether or not they have been solved. So let's actually run this algorithm on n equals 10. So let's see how this algorithm would perform if we're doing optimal change for 10. So now let's think about n equals 10 and run the top-down algorithm. All right, so how does this work? Well, we call change of 10. That's it. I mean, we do the initializations as described higher up in the notebook, and then we call change of 10. Okay, so I'm going to illustrate this in terms of a tree, and my tree is going to look like this. It's going to have a 10 at the root, and then this 10 is, I mean, this represents the call change of 10. Okay, so that's what this is. And then each time I have a call, it's going to generate potentially more calls, right? So when I'm trying to identify change for 10, what my algorithm does here in this while loop is it says I need to identify optimal change for 3 other values, right? For 9, for 10, for 7, and for 6, right? Which is 10 minus 1, 10 minus 3, and 10 minus 4. Okay, so what does this look like? Well, to identify optimal change for 10, I've got to figure out optimal change for 9. I've got to figure out optimal change for 7. And I've got to figure out optimal change for 6. Okay? And this is as written. And so strictly speaking, the way the algorithm is going to work is the first thing it does is it makes this recursive call here on change of 9. Change of 9. And when it does that, it sends us down this branch, and then we have to chase that branch. Okay? And then eventually we'll bubble back up. As I write the recursion tree, I will write each of the branches just to keep track of it for myself. But that's not precisely how the call stack might work in this example, if we were to actually implement this. And of course, you'd have some variations depending on architecture things. Okay, so we've got 10 asks for optimal change for 9, 7, and 6. So then we've got to go find optimal change for these. And so then how do we do this? Well, 9 asks for optimal change for what? For 8. For 9 minus 3, so for 6. And for 5. Okay, then 8 asks for optimal change for 7. For 5. And for 4, 7, and my table is going to get all squished here. My tree is going to get all squished here. So 7 asks for optimal change for 6, for 4, and for 3. 6 asks for optimal change for 5, for 2, and for 1. 5 asks for optimal change for 4, and for, let's see, for 5 minus, oh, I messed that up. So 6 is asking for optimal change, and that would be 3 and 2. So 5 is asking for 2, and then 1. 4 asks for optimal change for 3, 1, and 0. 3 asks for optimal change for 2 and for 0. 2 asks for optimal change for 1 and for 0. And 1 asks for optimal change for 0. Okay, so this is the far left branch of our recursion tree. And you know, it's deep. we go pretty far down on our first set of recursive calls. But all of these, well, not all these necessarily yet, but at least this one, the far left branch has now hit a base case, right? Our base case is 0. And how do I know that's the base case? I know it's the base case because in my initialization of my arrays, I've initialized n of 0 to equal 0. Okay, so n of 0 is 0. So now what do we do? Well, all the way down here, we say, okay, this one is in our table. Okay, so now we can push up. And so now what does that mean for it to be in our table? Well, it means that we've identified the answer to this one. Okay, so now 0 and 1 are now both written into our table. Okay, so now to find 2, all we have to do is find 0. Oh, and 0's already been identified. And so I'll write green to say, oh, it's already been identified. So we don't have to reprocess 0, we just look it up in the table. Okay, and so through all these, green means already solved. Solved, look up in table. Okay, as soon as I draw a blue box around something, that means we just solved the problem here, and then we recorded the solution in the table. So blue means solved here, solution recorded. Recorded in table. Okay. All right. So here we are. So 0's been solved. 1's been solved. 0 actually begins solved. So we might as well circle that in green. So now 2 is solved because we've got all of its leaves of its recursion tree. So that's all done. So then 3 is easy because we already know 0. 0 is already known in the table. So 3 is solved. Okay, so now once 3 is solved, then we ask about 4. We're just bubbling back up the recursion tree, like answering the questions that we saved to ask later. So now 4 can just look up its solutions in 3, in 1, and in 0. So now 4 is solved. So now 4 is solved here. 5 now, we're asking the question about 5. Well, 5 can look up its solutions in 2 and 1. And so now 5 is solved. 6 can look up its solutions in 3 and 2. Those are already done. So now 6 is solved. 7 can look up its solutions in 4 and 3. Those have already been done, so 7 is done now. And now 8 can look up its solutions in 5 and 4. Those have been solved already. So there's 5 and 4. So there's 8. And now 9 can look up its solutions in 6 and 5. And so now 9 is solved. And now 10 can look up its solutions in 9, 7, and 6. So now 10 is solved. Okay. And so which subproblems did we solve? Right? Remember the goal of this top-down approach was to not solve all the subproblems. Well, you can just look down the branch of this tree and you can see, look, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Right? It goes all the way down. And even though we were trying to avoid having to solve all those problems, we did. Inadvertently, we did. Even though maybe possibly they weren't all relevant. So which subproblems were actually solved? All of them. Right. In the end, we didn't save ourselves any work. So we could have a discussion about how to refactor this approach to be a little bit smarter and think about how we could identify the correct answer more quickly. And it's true, we could actually make it so that the recursion tree is not as deep. That would actually be fairly straightforward. Notice that what we essentially did is we did a depth-first search on the recursion tree, but we could have done a breadth-first search. And so maybe it's worth actually working through a quick breadth-first search on this recursion tree just to see what it would look like and see if it would save us any work. But I hope that it's becoming evident that we're not going to have huge gains, or we're highly unlikely to experience huge gains due to a top-down approach on the coin change problem. But real quick, let's see what a breadth-first search of the recursion tree would look like. And so what a breadth-first search is going to do is it's not going to chase all of these things down, and instead it's going to kind of keep track of problems to solve in a more systematic way. All right, so I've drawn out the recursion tree to a depth of 3, just to illustrate some of the issues that might arise. So now, what we could do is we could look at this recursion tree and we could say, hey, which of these problems, if we solved them first, would give us the answer soonest? Right? Never mind how we would identify those problems ahead of time in an algorithmic perspective, but which of these would give us the answer that we're looking for? And so, it's clear that we already have, just by default, we already have the answer to anything that says 0. So now what if we said, let's be a little bit clever and also assume that we have the answer to anything that has a 1. So what if we just assume that in designing our algorithm, we know, like it's clear from the outset, that optimal change for 1 is just 1 coin. Right? Then what we can do is we can put green boxes around all the 1s and 0s that are leaves of this recursion tree. So what does that give us? Well, all the way over here on the right, that gives us the ability to compute optimal change for 2. Okay, so now once we have optimal change for 2, we can go and fill in all the 2s. So now we can fill in that 2, we can fill in that 2, fill in that 2, fill in that 2, fill in that 2, and fill in that 2. And I think that's all the 2's. All right, so now once we have optimal change for 2, we can say, you know, what's the next thing that we could identify? Well, we need to be able to compute optimal change for 3. So what is optimal change for 3? Well, 3 is depends on 2 and 0, so we've got it. Right? So let's just say we got optimal change for 3. So once we have 3, then we can fill in all the 3's. We can say any 3 remaining in here is now considered a solved problem. And that's all of those. And so now we say, okay, what does it take to do the next step? Well, the next step would be computing optimal change for 5. Well, optimal change for 5 requires optimal change for 4. Do we have enough information to compute optimal change for 4? And yeah, we do. It's over here. Right? This 4 has all of its leaves filled in. So we're good to go. And so now we can say, yep, now we have identified optimal change for 4. Okay, so now once we have optimal change for 4, that lets us do 5. And so now we can box all of our 5's. And you can see the pattern, right? It's going to be very difficult to come up with any gains because no matter what we do, to solve the subproblems that we need solved, I mean, we can't do this without solving the subproblems for 9, 7, and 6. And we can't solve the subproblem for 6 without doing everything less than it, right? 6 depends on 5, 3, and 2. And 5 depends on 4, so there's nothing we can do to avoid solving 4, and certainly we have to solve 2 because that underlies a whole bunch of other things. It underlies 3, and it also underlies 6. So, you know, in the end, what we end up with is a situation where we're still going to have to solve all the subproblems to be able to identify a solution to the overall problem. So this is a fairly lengthy explanation for why it's not just a slam dunk to convert your DP algorithm into a top-down implementation. Right? You may end up kind of being stuck solving all the subproblems anyway. Right? There's no more 8's in there. Here's a 9, and now finally, because we have 9, 7, and 6 identified, now we can solve 10. And so we didn't end up with a very deep recursion tree, but we did still have to use a lot of memory to save, you know, as we were doing this breadth first search, to save exactly which problems we were in the middle of solving. So, you know, this is a little bit vague what I've drawn here in this wide, shallow tree. And I don't want to give you the impression that I have provided enough information for you to be able to implement this in code. You know, this top-down approach, you know, this top-down code that I gave would result in that recursion tree. The recursion tree I've drawn here is not supported by the code I wrote above. You would need additional logic to force the tree to fan out like this. But in any case, it doesn't save us anything because we still have to solve all the subproblems. And so even the extra effort that I went to think through this wide recursion tree didn't give me any algorithmic advantage, at least any very clear algorithmic advantage. So my takeaway here is that top-down in coin change has no grand advantage. Okay. Coin change has no grand advantage. And if you're very astute, you might be able to see, you might notice that there is a way, in principle, to avoid solving the subproblem for 4. If you're very clever and you take a very aggressive approach to this, you may be able to avoid solving the subproblem for 4. But I'll leave it to you to identify what the issues are in that. And so I encourage you to sit down and think about how would you write an algorithm that does this breadth first search recursion and then terminates as soon as possible without solving unnecessary extra problems.